Last week we discussed propositional logic and we discussed some examples for that as well. Today we are moving into predicate logic, which you may have studied in discrete mathematics again. So the reason why we are going from propositional to predicate, the reason for having something called predicate logic is that when it comes to propositional logic, there are certain limitations. So as you can see here, now say for example, Hashan is a UCSC student. Okay. Now when we look at it, you have a particular object who's involved in this statement. At the same time, there's a context. There's a property which the statement holds. Yeah, Hashan is a student from UCSC, not anywhere else. So there's a property or there's a context to this statement in addition to an object. But the thing is, when it comes to propositional logic, we will have to represent this entire sentence using a preposition like P or whatever. When we do so, these two things, object, property කියන දෙක, those two become invisible. They become hidden inside the propositional variable. Okay, it doesn't come out explicitly. If we take another example, if we say every student is younger than some instructor, so here you have some additional context where they say every student. So it's, when you take the students, the entire set of students, then they're younger than an instructor. Okay. And then there could be a scenario where you say some students, maybe not all, so some students are younger than an instructor. So words such as every or some, okay, and then these type of what do you call comparisons, those are not captured when it comes to propositional logic. Therefore, we need something which can do so, and that is why we move into something called predicate logic. Okay, predicate logic, or in other words, we call this first order logic. So in first order logic, we will be capturing the object plus the context with the property of that particular sentence. Right? So let's say, for example, okay, so look at this. You have objects. So whoever is involved in that statement is the object. Then you have the predicates, the property of the term. You have variables, connectives. These, of course, you know, variables and connectives. And then finally, you have a quantifier in predicate logic. So what are quantifiers? This is what we mentioned earlier by saying every and some. When you say every student is younger than an instructor, and you say some student is younger than an instructor. So these two quantifiers can be captured when it comes to predicate logic. So if we are talking about an every situation, we call that a universal situation. So it's true for everyone who's involved, universal. And the symbol we use in predicate logic for universal statements is this. An A which is upside down, which is turned upside down. Then when it comes to some, meaning not everybody, it's just some people. Some people, the statement is true for some of the people in the group, not for all the people. That is called an existential. That is an existential case. Okay. So if we are using an existential case, then the symbol would be this. Okay. So let's take an example also and see what this actually says. Let's say if we have to use predicate logic to represent that X is a student in UCSC, okay, if X is a student in UCSC, then what do? We represent this as, now we are using predicate logic, not prepositions, okay? So in predicate, what do? We say, okay, student X. What does this mean? This means that X is a student, okay? Or simply you could just say SX, anything. So what does this predicate say? It says that X is a student. So this is a universal case. Universal, or in other words, we have generalized this to all the students in the what do you call that, university. Okay, so it's true for everybody. But what if we are trying to instantiate that, which means ekkenekku gannawa, මේ pool එකෙන් ekkenekku gannawa, let's say Andy is a student in UCSC. So this is an instantiation. Which means we have picked one out of the pool and we are saying, okay, X is now Andy. Which means we can represent this by saying S Andy. Andy is a student in UCSC. So this is the universal case. ඕකම ගන්න පුළුවන් අනිත් පැත්තට in the existential case. If you say that there are some students in the pool who are from UCSC, in that case you have to use the existential case, not the universal case. Okay, we look at some examples in when we go further. Now you can have, when it comes to predicates, okay, now this is a predicate. When it comes to predicates, you can either have unary predicates, unary කියන්නේ එක්කෙනයි. Okay, there's just one variable, a unary predicate, or you can have a multi-arity predicate as well. Multi-arity කියලා කියන්නේ මෙහෙම එකක්. So let's say, for example, X is the father of Y. Okay, in a statement like this, how do you represent this? So you have father. Inside that you have to say about two people. X is the father of Y. So if we are if you're taking an instant out of this, saying, okay, Fred, there's some guy called Fred whose father is Y, then we can say Fred Y. Okay, we instantiated Fred out of the pool, right? So these type of predicates are called multi-arity predicates. So in this case, X and Y belong to the group of all men. Okay, that is how we define the set X and Y. They belong to all men. If that is the case, then there is an X who is Y's father, right? Now, if we want to represent something like this, say for example, there exists at least one man who is the father of Fred. Okay, Ekkenek hari innawa who is going to be the father of Fred. So how do we use this part? Who is the father of Fred? How do we do that? F Fred Y, yeah. And then how do we capture this part? There exists at least one man. Now this is not a for all statement. මෙතන කියන්නේ for all men කියලා. මෙතන කියන්නේ there exists. That means we are going for existential quantifier. There exists at least one person, which is to say, we're going to say there exists some y such that y is the father of Fred. Okay? There exists some y such that y is the father of Fred. If we take a universal quantifier statement, say you have something like this. Okay, say you have something like this. Then here you have a for all. Yeah, so this is a for all statement. මෙතන exists කතා නැහැ. මෙතන තියෙන්නේ ඔක්කොම ගැන. මෙතනට E આવොත් තමයි you have for all. Sorry, there exists. මෙතනට A આવොත් it is for all. So for all people, say X belongs to the set of all people. Okay? For all people, what do we again? Man X. Let's say man X කියලා කියන predicate එකකින් කියන්නේ that X is a man. Mortal X කියන predicate එකකින් කියන්නේ that X is mortal. Okay? So for all people, if X is a man, if එකක් ආවේ because of this implication. Okay, so if X is a man, then he's mortal. Yeah, this is what this predicate says. In other words, if we convert this into simple English, මෙතන කියන්නේ all men are mortal. If you are a man, you're mortal, which means all men, I mean for all people, if X is a man, then he is mortal, which is to say all men are mortal. එතකොට දැන් අපි මේකට summary එකක් ගත්තොත් to sum up it all together, for all X Px වගේ තිබුණොත් දැන් මෙතන Px තමයි predicate එක, all X කියලා කියන්නේ මේ quantifier එක. So for all X Px means that Px is true for all X. X කියන set එකට අදාළ වෙන හැමෝටම Px කියන predicate එක true වෙනවා. On the other hand, for some X Px කියලා කියන්නේ there exists some X such that Px is true. Okay, there exists some X such that Px is true. Okay, let's try an example in the tut. Where's the tut? Okay. Okay, look at this tut. Look at question number 10 here. Translate each of these statements into logical expressions using predicates, quantifiers, and logical connectives. Okay. So look at this. Cx denote the predicate X is in the correct place. So you have Cx to say that X is in the correct place. then Ex denotes that X is in excellent condition. Tx denotes that Tx denotes X is a tool. Okay, Tx says that X is a tool. Right, now come to this. The first statement says that something is not in the correct place. Now we are supposed to convert this into a logical expression using predicates and quantifiers and stuff. Then මෙතන something කියන්නේ මොකද්ද? Something says, okay, this is a bird. I mean, that's the quantifier. Yeah, something, hari for all, hari මොකක් හරි આવොත්, so that is a quantifier. The rest of it is what we first want. Not in the correct place. Then correct place එකේ ඉන්නවා නම් it's going to be Cx. Yeah. So if it is not in the correct place, which means this is a not. Then something. Something means ඔක්කොම නෙමෙයි. Just some x. So what is x here? They say, suppose that the domain consists of all tools. So x basically means all tools. X denotes all tools. In that case, Cx means x is in the correct place. So if it is not, then we put the not in front. And this is not true for all tools, it's just true for some tools, therefore we put the some x. Then look at part B. All tools are in the correct place and are in excellent condition. Okay, all tools, ඔක්කොම tools are in the correct place and are in excellent condition. Hari. Then බලන්න correct place කියන්නේ Cx and are in excellent condition කියන්නේ Ex. So that part is clear. They say all tools. Again, we have a predicate to say that X is a tool. Yeah, which means here they say all, all tools are in the correct place. So for this to be true, it has to be a tool. So if it is a tool එකක් නම්, then they are going to be in the correct place and in excellent condition. And this is true for all x. Yeah. මේ කියන්නේ for all x, okay, for everybody, for everything, if that is a tool, then it is in the correct place and in good condition. That is what they say here by all tools. So you have to use this Tx part to say, okay, it is a tool. Right, then everything is in the correct place and is in excellent condition. Now they don't specify anything. They don't say X is a tool or whatever. Now they are saying everything. We don't mind whatever it is, everything. So for all X, is in the correct place and is in excellent condition. But here we have an additional condition saying it's a tool, all tools. Final one, nothing is in the correct place and is in excellent condition. Nothing, correct place and in condition, correct place and good in is going to be this. Okay, but nothing is in that position, therefore not. And nobody, that means we are generalizing it to everyone, right? So for all x, nothing is in good condition and in the correct place. Okay. So I hope that's clear. Now let's go to this one, the 12th one. So here, all the predicates that we used were unary predicates. Okay, unary ones. Okay, now come to the 12th. Look at this. Use quantifiers to observe the statement. There is a woman who has taken a flight on every airline in the world. There's a woman who has taken a flight on every airline in the world. I don't know, then okay, we have to define our predicates, we have to define our logical variables, connectives, this and that. Okay. Okay, now what does this say? There's a woman who has taken a flight on every airline in the world. So let's say that first this part, a woman has taken a flight. Yeah, so what does PWF mean? This means that W, the woman W, has taken a flight. Let me say that W is in the set of all women. All women. Okay. F says all flights. So WF means woman W has taken a flight F. Okay. Then let's take R and say that flight F belongs to airline A. F belongs to airline A. It says there's a woman who has taken a flight on every airline, which says woman has taken a flight and the flight belongs to a particular airline. So here A is the set of all airlines. Okay. Now how do we represent this statement? There's a woman, so let's forget about the there's a part for now. That first part. Okay. A woman has taken a flight on every airline, which means this woman, WF, woman has taken a flight while the flight belongs to an airline. Yeah, woman has taken a flight and the flight belongs to some airline, we don't know what it is. Now, they say, there's a woman, which means there's at least one woman, ekkenek hari innawa. එක ගෑනු කෙනෙක් හරි ඉන්නවා who has taken a flight. මොකක් හරි flight එකක් අරගෙන තියෙනවා හැම airline එකම. ඒක මොකද අපි quantify කරන්නේ? There is a woman. අඩු ගානේ there's one woman who has taken අඩු ගානේ one flight on all airlines. Did you understand that? Remember that in a compound statement like this, when you get the sum in front, right? Sum එක ඉස්සරහා තියනවා කියලා කියන්නේ sum කියන්නේ මේ existential එක ඉස්සරහා තියනවා කියන්නේ that means there's at least one such case for which this predicate is true. අඩු ගන්න එකක් හරි ඉන්නවා. Okay? Sum කියන්නේ in general what we say is there are some cases where the predicate gets satisfied. Okay? But just remember that when sum is in front, it's that there's at least one such case, ekak hari, so that that particular thing is true. So there is a woman, there's at least one woman, there's one woman who has taken a flight. She has taken some flight, so not all flights, some flights on every airline, on all the airlines. Okay, so we captured the what do you call quantifiers, and then we have the predicate over here. Okay, right. Now, shall we go to
Excuse me.
yeah?
අපි මේ ඔතන for all f1යි or for existential effect.
Instead of y, you are going to replace that with Jerry. Okay, so X loves Jerry, and who is this for? This is true for all the people. Okay, second one says everybody loves somebody. So you have everybody. Okay, so all people are going to love someone. Doesn't have to be everyone, but they do love somebody. Okay, which means LXY. But what is the set that this is true for? Everyone, all X is going to love someone. For every person that you take, there's going to be someone whom they love. And then look at the third one. There's somebody whom everyone loves. That means there's this one person whom everyone loves. Okay, so there's one guy. So X loves Y. Okay, but there's just one person whom everybody is going to love. Okay, there's one guy, some X, whom everyone likes. There's somebody whom Lydia does not love. So what does that mean? If Lydia loves somebody, how do we do that? Lydia. Okay, Lydia loves Y. Okay, so this means Lydia loves Y. But what does this say? It says that there's someone whom she does not love. So she's not going to love someone. So there's someone whom she's not going to love. The next one is also a bit similar. There's someone whom no one loves. There's one guy whom nobody likes. So LXY means X loves Y. Okay, if you put a not, that means X doesn't love Y. So there's this one person, there's one guy whom nobody, when you take everybody in general, there's one person whom they don't love. So that is captured by this. Okay, now to come to the next one. There is exactly one person whom everybody loves. Now this is a bit different. because it says there's exactly one person. Now the part E reads that there's someone. Okay, there's at least somebody whom nobody loves. Part F says there's exactly one person whom everybody loves. That means there's just one. එක්කෙනෙක් විතරයි ඉන්නේ, ඊට වැඩි කවුරුත් නැහැ. And everybody loves that ekkena. Okay, so how do we do that? Now, if this is the set of people, okay, there's one guy whom everyone is going to like. And we have to, what do you call, conserve this property. Exactly one person. We also have to say that may ara tava kawurut naha කියන එක. Which means if there is somebody else whom people love, then we have to say that මෙහෙම කොටුවක් ඉන්න බෑ. So this කොටුව has to either be, I mean this කොටුව has to be equal to this guy. Because there cannot be another one whom they love. Because there's just one person. So how do you represent that? There's one guy for everybody whom everyone likes. There's one guy, there's a guy whom everybody loves. But මෙතන නවතින we have to say that තව එක්කෙනෙක් නැහැයි කියලා. So how do we say that? We have to say make a and. In case if there's another guy whom they love, if there's a guy Z that people love, for all Z, if X loves Z, then if that is the case, then we say that Z should be equal to Y. Did you get it? So you say, okay, there's some guy that everybody loves, and then you have to capture the other part. You say that, okay, that and if in case there's another guy, then for all of those guys, if X loves them, then they are that guy is equal to the previous guy. There's no other person. Then FG, part G, there are exactly two people whom Lynn loves. Now, Lynn, there's Lynn. Lynn loves exactly two people. Then a type. So Lynn likes two people, and in case if she likes the other one, then we have to say that the other one is either this one or that one. Yeah? Okay, so what do we do? Lynn is going to like Lynn. So Lynn loves the other one. Okay, for all X and all Y. Lynn loves X, and Lynn loves another one as well. Lynn loves Y. Yeah. These two are the people whom she loves. We also have to say that if there is a third person that she likes, then that third person is either X or Y. So we say and in case if Lynn likes a Z for all Z, if she likes a Z, then that guy is either X or that guy is Y. Did you get it? So she likes two people, and if there is a third, then that third cannot exist. Therefore, we say that if that is the case, then that third is equal to the previous, either one of the previous two. Okay. We can leave it. Okay, now come to question number 2. Question number 2. It says that X is a, no, every girl in Constantinople lives in Istanbul, not Constantinople. And you can, so every girl in this Constantinople, and you can, so X, first we need to say that our predicates are, okay, X is a girl, okay, so that's going to be one predicate. Then it says about this girl living in Constantinople or this girl living in Istanbul, right? Therefore we say that X lives in Y, LXY. Okay, then what does it say? Every girl in Constantinople. So for all X, so for all X, every girl in Constantinople, like again make plus, she lives in Constantinople. She is a girl plus she is in Constantinople. Every girl in Constantinople lives in Istanbul, not Constantinople. This girl in Constantinople, if this is so, if she is a girl and if she is in Constantinople, then what do they say? She lives in Istanbul. This guy lives in Istanbul, not Constantinople, and not in Constantinople. Did you get it? When you take everyone for all X, if she is a girl and if she lives in Constantinople, then she is actually in Istanbul and not in Constantinople. Why do we use and here? Because they say that she lives in Istanbul but not in Constantinople. That's why we use an and in the connection rather. Okay, now come to the next one, the third question. Everyone walks or talks. Okay, so for all X, they either walk or they talk. Okay, part B. Every student walks or talks. We need another one. X is a student is Sx. Okay, so they say X, every student walks or talks. What does that mean? For all X, every student, so we have to say that X is a student now. Okay, every student, if X is a student, then what does she do? Not she or he, walks or talks. Walks or talks. Every student walks or talks. Then come to it should also come to the under the third one. Okay, A, I'll make it C. Every student who walks talks. What does that mean? Every student who walks, every student, so it's an Sx, who walks, may Sx and may Wx. Every student who walks, then he or she talks. Okay. Every student who walks, then he is going to talk. Okay, now come to the fifth question. Okay, for all n, for all natural numbers, there's some natural number. Okay, for all numbers, there's some number. And what does this part say? That En is, what is it? Oh, n is even. Okay, n is even. If n is not even, then it is not En. Yeah. So here n is not even, which means n is odd. Okay, so this represents odd numbers, right? Then it says n is not equal to m, which means අපි දැන් මෙතන කතා කරන n නෙමෙයි වෙන කෙනෙක් ගැන මේ කියන්නේ. So n and m are different. Okay, so when the number is an odd number, okay, there is a different number to this, okay, such that what does n plus m mean? The addition. En plus m means it's even. Addition is even. What does that mean? For all numbers, for all natural numbers, there is some natural number. ඔක්කොම natural numbers ගත්තාම there is someone where this natural number is odd, okay, and there's this other natural number which is not equal to the number that we referred to earlier, where these two people, when we add them together, their sum becomes even, right? So basically what this means is for all odd numbers, all the odd numbers have a different for all the odd numbers there's a different number such that these two numbers addition is going to be even. Okay, so if you take for all odd numbers, any odd number, there's a different natural number where the addition is going to be even. This means that there is some some natural number. ඔක්කොම නෙමෙයි. මෙතනට ඕන එකක් දාලා හරියන්නේ නැහැ. There is somebody. ඔක්කොම ගත්තාම කවර එක්කෙනෙක් ඉන්නවා. Rather than addition becomes odd, even. Right. Then come to the B part. PM means n is prime. Okay. Pn means n is prime. So what did this say? M, n are prime. Yeah. This means m and n are not 2. There are 2 prime numbers and these 2 prime numbers are not 2. Okay. In that case, their addition is even. And this is true for all the natural numbers. Natural numbers as in when we go inside the bracket, they become all prime numbers. Yeah. When you take 2 prime numbers, any 2 prime numbers, because it is true for all. When you take any 2 prime numbers which are not 2, in that case, the addition is going to be even. So how do you simply represent this in English? You could say that any 2 prime numbers which are not 2 produce an even addition. Sum of any 2 prime numbers except 2 is even. Right? Okay, now come to the 6th question. Give the 6th question a try. First one says, okay, sum x, there's sum x, okay, where x is my friend, but that x is not perfect. So how do we say that? There exist some friends who are not perfect. Like this. Okay, there exist some friends who are not perfect. Then part B, again we have a there exists some people who are not my friends but they're perfect. Okay, so there exists some people who are not my friends but they're perfect. Then part C, again there exists and they're not my friends and they're not perfect also. Okay, there exist some people who are not my friends and are not perfect. Final one. So here the there exists has become a negation. So this entire statement is a not. There's nothing which satisfies this. So what does this mean? Friend x and perfect x. So if we take this part, what does that say? There exist some friends who are perfect. There exist some friends who are perfect. Then there exist some friends can අඩු ගන්න එක්කෙනෙක් හරි ඉන්නවා මගේ යාළුවෙක් සහ යා perfect. ඒක ඉස්සරහට not එකක් එනවා කියන්නේ not එකක් එනවා කියලා කියන්නේ මොකද්ද? There exists nobody who is a friend of mine and who is perfect. ඒ කියන්නේ nobody, none of my friends are perfect. When you encounter these type of things in the questions, even in logic programming and stuff, you get sometimes these type of things. So you write the case where it is true for one case, okay, and if you put the negation in front of it, that means there's no one who satisfies these predicates. Okay. Right. Now, okay, in the seventh question, what we have is using inference rules. So how you simplify statements in predicate logic using simply inference rules. Okay. Before we go to that, let's look at parse trees. You have parse trees in this as well. Okay. Right. So when you draw a parse tree, just like we did last week, what we do is we start from the outermost operator that you have. In this case, it is all x, the quantifier, which is outermost. Okay, so it goes as the first node. Then you come inside. Okay, when you come inside, then when you take this part, who is responsible for the division of that? This AND. This AND divides this section from this S section. Yeah. So we get the AND. Okay. So to the right hand side of this AND, you have SXY. So you have the S and then the variables XY, the parameters. And then to the left hand side of the AND, you have two predicates, PX and QX. How do we separate them? They're separated through this implication. So you have the implication, you have P and Q, and then the parameters involved into these two predicates are X and X. So you have X in this, okay? So in the leaf nodes, you have your parameters, your variables, and the other nodes, you have your operators and the quantifiers and the predicates, okay? Okay, let's come to this. So how do we draw the tree for this? The outermost quantifier is sum x. Okay, you have sum x, and then inside your pair of brackets, who divides your set? This AND. Yeah, you have a left hand side and a right hand side. So you have your and divides and separates P from the rest of it. So now we have the rest of it, which is this. Who's the outermost guy here? Is all y. Yeah. Then when you come inside the pair of brackets into this, you have your O. Okay. O separates a left and a right. On the left, you have negation QXY, negation operator Q, X and Y. On the other side, you have P, Y and Z. Right? So this is the parse tree for this example. Okay. Now, there's one other thing which we need to talk about, and that is which we mentioned at the beginning of this discussion, Generalization instantiation, if you remember, we discussed something like that. Okay, so these also come under rules of inference. Okay, last week we discussed some rules of inference. In addition to that, today we are going to add some inference rules for predicate logic into those into that list. Okay, so we have something called, like we did in the beginning, universal instantiation. So what do we do here? For all x px එකක් තිබ්බොත් අපිට හරි for all x px is true කියලා තිබුණොත් අර අපි කලින් කතා කළා වගේ for example x is a student of UCSC කියලා තිබුණොත් we instantiate that to p and d or something. Yeah, so මේක instantiate කරලා අපි ඔන්න මේක instant එකකට හදාගන්න එකට අපි කියනවා universal instantiation. And what is the symbol for this? The symbol is for all x e. Universal instantiation for all x e. Okay. ඕකම අනිත් පැත්තට තියෙනවා existential instantiation. That means when you have the sum, okay, so when you have sum x px, you say pc. So this c is, it stands for some element c. So here, what is the symbol you use for sum x e? Then, just like you instantiate, you have the opposite as well. You have generalization. Then general තිබ්බක් instantiate කරනවා වගේ instantiated එකක් generalize කරන්න පුළුවන්. හරිද? ඒතර ඒක යන්නේ universal generalization. So what happens here is you have PC, C connector, you have PC true. In that case, you can generalize it saying okkoma x lata it is true. Right? So the symbol here is for all x you introduce. Similarly, you have the other thing as well for existential generalization. So first, for some c, for an arbitrary c, if you say c is true, pc is true, then you say, okay, there is some x where our predicate px is true. This existential generalization for all xi, sorry, for some xi. Okay. Okay, so these four inference rules plus the inference rules that we discussed last week, everything is there. And now let's come to question number 7 to see how we can use them. Show that the premise, a student in the class has not read the book. Everyone in this class passed the first exam, imply the conclusion someone who passed the first exam has not read the book. Okay, so we have two statements. A student in this class has not read the book. So x, okay, a student in this class has not read the book. First of all, we have to say that, okay, this guy is a student in the class, yeah? That's a context. X is a student in the class. So let's say it is Sx. Ready? Has not read the book. So we say X has read the, let's say this is Rx. Everyone in the class passed the first exam. X passed the first exam. px. Imply the conclusion someone who passed the first exam has, okay. Right, now let's write our premises. So what is our first premise? A student in the class has not read the book. A student. Again, me okkoma lamainta neme, for some lamai. So we say for some, if that guy is a student in the class, a student in the class has not read the book. So this guy is a student in the class and he has not read the book. For some, there are some students in the class who has not read the book. Everyone in the class passed the first exam. Then for all, when you take everybody in the class, for all, if they are in the class, everyone in the class passed the first exam. So if they are in the class, then they pass the exam. Okay. Now the thing is, if it is a bit confusing to find out the operator which comes in these type of scenarios, student in the class has not read the book or a conjunction the implication though conjunction implications. If it is a bit difficult to process that, then just remember that normally, usually with some x, what you get is the conjunction, and then with all, with for all, what you get is the implication. Okay, this is useful for logic programming as well in the next semester. Okay, so use that, and then your conclusion is someone who passed the first exam. Someone, not all. So someone who passed the exam has not read the book. Mea passala sahaya pota kiyawalat ne. This is our conclusion. Okay. Right, let's give this a try to get this conclusion. Okay, so let's take the first premise. For some x, sx, and negation rx. So this is my premise. Then remember that okay, you can't generalize these and solve this. You have to instantiate it anyway. Instantiate when you get the conclusion, you generalize it and say, okay, general case make a true. So what I'm going to do is I'm going to instantiate this. This is existential. Therefore, I'm going to use existential instantiation here. For whatever arbitrary variable, this is true. So this is existential instantiation. How do I imply? The notation is for some x e, and I use the first premise for this. Yeah. Then let's take the next one. For all x, sx implies px. Make a premise. Number 4, let's instantiate this. SA implies PA. For that arbitrary A, this is true, and this is universal instantiation. For all x, E3. Right? Okay, now you have these. Now what do I want to do? I want PA and negation RA. Right? Okay, first I'll go to this second one and take this SA out. හරි කොහොමද SA out ගන්නෙ? Using the last week's inference rules, we know that when you have an AND, you can perform simplification, right? So let's take SA from that. I used simplification here. What's the notation for that? And E, elimination. Which one did I pick? I picked the first one. And the inference rule, sorry, the premise I used was 2. Okay. Then number 6. Since I have SA, here also I have SA, so I can take this PA, right? What is that rule? That's modus ponens from last week. PA. කොහොමද ගත්තේ modus ponens වලින්? ඒ කියන්නේ implication, elimination. Which one did you pick? You picked the second one out of the two. Yeah, and the statements you used were 4 and 5. Hari. Then you have PA here. Okay. Now go back to the same rule. Number 2, this one. Now I'm going to take RA out. Okay, take negation RA out. What is that? Again, that is simplification. So and E, I took 2 now, and this is using the second one. Yeah. Okay, now what can I do? I have these 2 predicates to be true. If 2 predicates are true, then what did we say? We can connect them using conjunction, right? That's again a simple inference rule. So connect these 2 in conjunction. So this is and I using 6 and 7. Okay, now you have your answer. You have gotten it, but it's an instantiated case. Therefore, you need to generalize it. Now you can use the existential method. So you can use the existential generalization, saying there are some cases when this is true. Okay, this is existential. Existential generalization of number 8. Got it? So this is how you simplify it using the inference rules and
okay, I have a question.
the answer. Yeah, go ahead, please. Negate thing. You say you can take a normal statement for some, and you put the negation to the predicate. Predicate negate karla for some, and අනිත් පැත්තත් හරියනවා. When you have for some negation එකක්, ඒ කියන්නේ මොකක්වත් නැහැයි කියන එකට තිබුණොතින් you can take for all එහෙම එකක් නැහැ කියලා. හරිද? So these two are negations. These two are negation statements, which these two are usually used when it comes to expressing things in English or expressing an English statement in logical expressions. හරිද? negation එක දාලා මොකක් හරි එකක් කියලා තියෙනවා, ඒක අනිත් පැත්ත හරවන්න පුළුවන්. ඔහොම එකක් දාලා අනිත් පැත්ත හරවනවා. හරිද? Something like that. For example, when you come to the final question in the activity, එකේ කියනවානේ පළවෙනි එකේ all dogs have fleas කියලා. හරි? ඕක අනිත් පැත්ත හරවන්න ඕන නම් අපි කියමුකෝ all dogs have fleas නේ. So in that case, if we want to represent that, if I say x is a dog is dx and x has fleas is fx, right? All dogs For all x, if you are a dog, you have fleas. Okay. So if you want to negate this statement and get the negated answer in English, මේකට අපි negation එකක් දැම්මුතින් what should I do? I take the negation into my predicates apart from taking it into the quantifier. හරි. එතකොට මේක මම ඇතුළට දැම්මහම dx fx මෙහෙම එනවා. Yeah. So before I go further, I'll just I'll convert this into an O format. We discussed this last week. P implies Q is POQ. So using this, what you can do is, this is dx and negation fx for some x. Yeah. So this is the negated version of your yeah, of this. Now when you represent this in English, how can you say that? You can say that this said that if you are a dog, you have fleas. All dogs have fleas. This reads as, there is a dog, for some x, there's a dog, okay? There could be a dog who does not have fleas. So that's a negated statement of this. You say for all, here you say for some, that statement එක හරියන්නේ නැති වෙලාවක් එන්න පුළුවන්. Okay, there could be at least one such case. Okay, so that is the negations of a quantified statement in predicate logic, right? So you might you might get a simple question to just negate that and write in English or something of that sort. Okay, we did those. Yeah, that is it. That is what we have to cover today. So now we have finished predicate, propositional and predicate logic. So that part is over. Temporal logic part, I think Sandurvan sir is the one who